All right, so let's look at some problems in this section 7-9 for ideal gases. And you know, if we didn't even know we were in this section, this is air, ideal gas. All right, so what if air is compressed from an initial state of P1 of 700, P1 of 100 kPa, T1 of 17 Celsius, let's change that to Kelvin, and a P2 of 600, and a T2 of 57 degrees Celsius. Determine the entropy change of air during this compression process using either the property tables or the average constant specific heats. All right, we're finding entropy change. We're finding S2 minus S1. I'm not going to use any of these PR, VR equations. I'm not going to use these equations. That's for isentropic. But I am going to use some of these. And I made a mess of these. I am going to use some of these. All right, so first we want to determine the entropy change using the property tables. So that is using these S naughts, right? That's using these S naughts. All right, so because this is air, I don't want these bars per mole. I want these per kilogram. So I'm going to use this equation right here. I know the P2 and P1. I can find the S2 naught and S1 naught from the temperatures from property tables. So I'm going to find the entropy change that way for part A, right? That equation right there. S2 minus S1. Let me write that. S2 minus S1. That's what I'm looking for. Equals S2 naught minus S1 naught minus R ln P2 over P1. R ln P2 over P1. So, from the property tables, A17, let me get this S naught and S1. Let's see. Let's go to the property tables. Table A17 for air. Yeah, and here's this S naught. All right, what temperature are we at? We were in Kelvin. We were at a T1 of 17, which is 290. We were at 290, and then we go to a T2 of 57 plus 273. You don't have to do 273.15, just do 273. So 57 plus 273, 330. So we're going from here to here. So there we go. The S1, the S2, right there. 1.797 minus 1.66802. All right, go back to our notes. So S2 minus S1 would be S2 naught was from property tables 1.79783 kilojoule per kilogram K minus 1.66802 kilojoule per kilogram K minus R. This is not the universal, this is the R for air. And the R for air, table A1, 0.287 kilojoule per kilogram K ln P2 over P1, 600 over 100, right? 6, ln of 6, or 600 over 100. This is unitless because it's P2 over P1. So there we go, and so there we've got we can write this as delta S as the change in entropy. Change in entropy would be this value, negative 0.3884 kilojoule per kilogram K. And it is okay to get a negative change in entropy because we're only looking at air. We're not looking at air and the surroundings and the universe. You know, yes, entropy is always increasing, but for certain processes, definitely entropy can and will decrease. So that was using these S naughts. Okay, what if we had used the average specific heats? What if we'd used, so this was A, what if we'd used this equation right here, S2 minus S1. All right, let's go back to our equations that we've written on a formula sheet. All right, so I've got this one and this one, right? I've got this one right here, and I've got this one right here. Which one should we use? Well, we don't know the ratio of the volumes. We do know the ratio of the pressures. I'm going to use this one right here. S2 minus S1 equals Cp at the average temperature, ln T2 over T1. All right, This would be Cp, the average temperature, natural log T2 over T1 minus R ln P2 over P1. So I'll say delta S, change in entropy, equals. All right, so I would go to table A2. I don't think I'm going to go there. Table A2 at what temperature? Should I do the temperature at 290 that I started at, or at 330 that I ended at, or the average temperature 310 Kelvin? I do kind of want you to interpolate. Sometimes they're so close together that you can estimate, or but this would be 1.006 kilojoule per kilogram K. This ln has to be the absolute temperature, is 330 over 290 minus 0.287 ln 6. You might have that number already in your calculator. Here we would get the delta S, negative 0.3842 kilojoule per kilogram K. So do you see how you get very similar answers, especially with just a small temperature difference? Then yeah, this Cp is probably a good estimation of the Cp. Okay, so that was finding the entropy change of air. Two different ways. Finding the entropy change of air for two different ways. All right, let's go ahead and keep on going with the next problem. All right, air, ideal gas, is compressed in a car engine from a temperature T1 of 22 degrees C, P1 95 kPa, in a reversible and adiabatic manner. Do you see these two things? If something is reversible and adiabatic, then it is isentropic. That was a clever way of them telling us this is isentropic. Remember, if it has two out of these three things, it is the third. If it's reversible and adiabatic, then it is isentropic. All right, so this is isentropic. I'm not going to find the entropy change. They tell me the ratio of the volumes is 8, determine the final temperature of the air. So this is an isentropic. So I can use either of those methods. The second half of these notes, I can use the relative pressures and relative volumes from the air property table, or I can use these equations right here if we want to assume constant specific heats. I'm actually going to do both, but let me start with this one, the relative pressure and relative volume methods. Okay, so if I know T1, then I can get either PR or VR, and then I can PR or VR1 based on the temperature. Then I can convert that to PR or VR2 and go get T2. Do I need to use PRs or VRs? Goodness. Well, I know the ratio of volumes is 8. So if V1 over V2 is 8, that's also VR1 over VR2. So let me use VRs. Okay, so for a temperature T1 of 22 degrees C, I'm going to go to table A17 and find VR1. All right. 22 plus 273, 295 Kelvin. So let me go to table A17. This is in Kelvin. 290. Well, look, we already have a 295 right there. Awesome. 647.9. 647.9. All right, so this would be 647.9. It is unitless, I believe. All right, so if that's the V1, what is the V2? Well, V1 over V2 is 8, so if this is 60, so 647.9, then this would be, solve for it, 80.99. I'm making a mess of this. 80.99. So for 80.99, what is the temperature? Probably going to have to interpolate. For this. May not go through the interpolation. Hopefully you all know that. So now my VR is 80.99. Let me go. Goodness. Okay. VR80.99 in between there. All right, in between there. So interpolate. I don't want you to estimate. I do want you to interpolate. I do top minus bottom over middle minus bottom equals top minus bottom over middle minus bottom. You can use interpolation in calculator. Interpolate to get the temperature and make sure that your calculator spits something out to you that's in between 660 and 670. You should be able to tell which one it's closer to. Should it be closer to 660 or closer to 670? Well, is 80.99 closer to 81.89 or 78.6? I think it's closer to 660. All right, see if you can do that. I've got 662.7 Kelvin. 662.7 Kelvin. If you want to subtract 273 to get it in Celsius, you can as well. So, all right, that is my preferred method. All right, but what if we had used constant specific heats? If we had used constant specific heats. Now, the trouble with constant specific heats is specific heat is not really constant, and so if we, especially if it's a large temperature range or large change in temperatures, then using constant specific heats could be a little bit off. This is I don't know, a fairly decent change in temperature, so this might be off by a little bit, but we'll see. All right, we have some equations here. We have some equations for ideal gas using constant. We have these three equations right here for an isentropic, ideal gas, constant specific heats. All right, I know the ratio of volume, so I know this right here, or I know this right here, so probably the top equation or the bottom equation. And I know the initial temperature, I'm trying to find the final temperature, so I think that makes sense that this is the equation I would use. T2 over T1 equals, now be careful, V1 over V2. T2 over T1, T2 over T1 equals V1 over V2 raised to the K minus 1. Now the K values we could get from the property table, from table A1, I believe, or possibly table, let's go to that real quick, A2 or A3. Where is the the K values? Right here, it's in table A2. Also here, table A2 as well. We're looking at air. We are looking at a temperature change from, well, we actually don't know. We know that we started at 295. So we could see this is 1.400 to 0.401. So we're starting at 295, and we really don't know where we're ending up at. If in general, if you know where you're starting, you don't know where you're ending up, we can just start with the K for where we're starting, and this is close enough to. I'm just going to do 1.4. It's going to do 1.4. All right, so let's go back to our notes. Let's use a K value of 1.4. So here we go. T2 that I don't know over 295 Kelvin equals, this ratio is 8 raised to the 1.4, so raised to the 0.4. I would get a T2 677.7 Kelvin. 677.7 Kelvin compared to 662. You know, a little bit off, but we're in the range, right? We're in the ballpark. Knowing that it goes up to this high temperature, we could actually redo this at the K at the average of 295 and 677, and we'd probably get a little bit closer to a better guess for 662. But I don't want you to do this twice. I just want you to take the value at the beginning property value. Okay, so for an ideal gas, for an isentropic ideal gas, we have two methods, the relative methods, or we have these other equations for constant specific heats these equations we've written on our formula sheet, we'll use to find, in this case we're finding the final temperature. Okay? These are tough. There's a lot of equations, a lot of different problems. You're going to have a lot of homework problems. I'm not going to go through, I'm only going through 3 problems right here with you in the notes. But practice. Use all those equations. You know, try to figure out how to put all those equations on your little 3x5 index card, front and back. All right, let's look at this one. Helium gas is compressed by an adiabatic compressor from initial state P1 of 14 psia, T1 of 50 degrees Fahrenheit to a T2 of 320 Fahrenheit in a reversible manner. Determine the exit pressure P2. All right. Did you see that it was adiabatic and reversible? It is isentropic. All right, it is isentropic. For isentropic, we have 2 methods. We have the relative method, but I don't think helium actually has relative pressure and relative volumes in the helium property table. So the only method we have are these 3 equations right here for isentropic, ideal gas. So we're going to have to assume constant specific heats. All right. We know the initial pressure, and we know the initial temperature and the final temperature. We're not told anything about the volumes or specific volumes. This equation right here is our best bet. We know P1, we know T1, T2. There we can use this to solve for P2. So that equation right there, T2 over T1, T2 over T1 equals P2 over P1 raised to the K minus 1 over K. Don't get too bogged down into this, right? If we could do this a number of different ways. If we're raising one side to the K minus 1 over K, sorry, let me go ahead and start plugging things in. T2 would be 320, but it has to be absolute temperature, whatever, 320 plus 460. T1 is 50 plus 460 equals P2 over 14 psia raised to the K. What is K for helium? K for helium, 1.667. So this would be 0.667 over 1.667. Solve for P2. If you want to get down to this, right? How can we get rid of that that exponent, right? If we have, I don't know, 7 equals x squared, we would square root both of them. What we're really doing is raise both of them to the 1/2 power. So if we raise this to the 1.667 over 0.667, 1.667 over 0.667, that would get rid of the exponent, right? All right, so, right, if you have something raised to the 2nd power, then raise both sides to the 1/2 power. So we've got, what we're really doing is we're raising both sides to the K over K minus 1, K over K minus 1. So kind of here's another equation right here. P2 over P1 equals T2 over T1 raised to the K minus 1, K over K minus 1. But again, you don't want to write so many equations on your formula sheet. Just know how to get into that mathematically to solve for P2. Okay, so there we go. Solve for P2. P2 would be 40.5 psia. 40.5 psia. Solving for P2 right there. So for this one, it didn't tell us it was isentropic. It told us it was adiabatic and reversible. So that means it's isentropic. For isentropic ideal gases, we have these equations right here. K value for helium, 1.667. All right, so practice, right? Practice. This section was all about ideal gases. But sometimes we were finding the entropy change of ideal gases. Sometimes it was isentropic. There was no entropy change, so we were finding the final temperature for ideal gases. Sometimes it's air, sometimes it's helium, oxygen, all those. Sometimes we need to use property tables, sometimes we can use constant specific heats. Lots of equations, lots of practice. Good luck.